Hello, everyone. Thanks for joining the webinar. Happy Diwali to all Indian participants. They had a big celebration yesterday. So hope you recovered from all the festivities. So this is our weekly webinar on geoenvironmental engineering, polluted land, waste management, and sustainability and resiliency. So we have been having these webinars since mid-January. So the purpose of these webinars is mainly to help graduate students and young faculty and professionals to understand the different geoenvironmental problems that we have worldwide, and then help understand, what research projects are going on, or even, the practical projects that are going on, and learn from them. A lot of these graduate students and faculty, they are looking into research areas to work on. So these webinars should help you identify new areas of research to pursue. And more than that, I wanted to create a good network of geoenvironmental engineering researchers. So a lot of participants are already, contacting the speakers and even other attendees. So I'm happy that this is really happening. We have webinars scheduled until end of this month, at the end of this year. After today's excellent presentation, we will have next week a presentation on reuse of water treatment sludge. And I don't want you to miss that, because a lot of researchers are doing research on beneficial use of different types of waste materials. So, you already know a lot of research done on some conventional waste materials, but, water treatment sludge is one thing that is generated almost everywhere. So how do we characterize that one? How do we use that one? So it's going to be a very interesting presentation next week. So same time, so please join that one. And then we have other presentations, as you see from this schedule. So they are on different topics and interesting. So also, the past webinars have been recorded. Go to this YouTube channel and view any webinars that you are interested in. I hope, we have 50 webinars in this one. Hopefully you will find at least one or two of your interest. So please check these out. For today's webinar, we have 547 registrants for this webinar. So I will recommend you to, mute your mic and switch off your video. Type your questions in the chat box at any time during the presentation. So at the end, our presenter will try to answer as many questions as possible. So thanks again for finding time to attend this webinar. So I want to just briefly introduce our webinar speaker today. So our presenter today is Dr. Kevin Foye. And Dr. Foye completed his PhD at Purdue University here in US in 2005 with research focused on reliability-based design of foundations. Since that time, he has performed further work to implement reliability-based design methodologies in geoenvironmental engineering, which is the topic of webinar today. Dr. Foye joined CTI and Associates Incorporated in Michigan after completing his PhD, and he has been working for several years there. Currently, he is serving as a senior engineer and geotechnical practice lead in the company. He has consulted to geoenvironmental engineering projects in 16 US states and 5 countries, all specializing in environmental geotechnics and landfill engineering. So his experience is really, very broad. So he has expertise in engineering municipal solid waste, hazardous waste, low-level radioactive waste, mixed waste, and coal combustion residual landfills, serving commercial, municipal, state, and federal government agencies. Dr. Foye's professional service while at CTI includes serving on the Geoenvironmental Engineering Committee of ASCE, Risk and Reliability Committees of ISSMGE, chair of various ASCE conference technical sessions, and currently is the associate editor for the ASCE Journal of Geotechnical and Geoenvironmental Engineering. Dr. Foye has published more than 30 journal papers and conference papers related to today's webinar topic, and he has instructed 5 graduate geotechnical engineering courses. So I have known Kevin for many years as a member of Geoenvironmental Engineering Committee of ASCE. I am very much impressed with his types of geoenvironmental engineering projects he works on, and he is very friendly and he's very thorough. I always had a pleasure of spending time with him and knowing him. So I'm glad that he accepted my invitation to give this webinar. So with that brief introduction, I'm going to stop sharing. Kevin, please start sharing and then present your webinar. Thanks again in advance for your time and effort in giving this webinar.
Yeah, thank you for that introduction. It all sounds very impressive when it's all put together like that. Well, good morning, everyone. Thank you for joining. And I'm looking forward to giving this presentation. And I will say in advance that we have a lot of ground to cover in a very short period of time. So what I'm intending to do with this presentation is to introduce a number of different topics related to the decisions that we needed to make on this project. And I would encourage you, if there's something that strikes your interest where you'd like to know some more information about it, please type those questions into the comments in the chat, and we will try to get to that as we're able as we move through this. So as it says in the title, this has to do with a case history of a very particular radioactive waste landfill closure project that I was involved in. And I call it a case history. It's a case history in the sense that I'm going to present what we did and how we were attempting to overcome a very particular problem, a lot of it related to regulatory acceptance. But it's not a case history in the sense that I have a lot of monitoring data after we implemented this particular solution. So if that was the kind of case history you're looking for, it's not exactly like that, but I think you will see how we arrived at the different decisions we did based on data from not only this site, but other sites. So very briefly, there's 3 main topics that I'm going to touch on. Very quickly, I'm going to talk a little bit about risk, and specifically risk as it relates to design decisions, and then the closure process under which this particular site was closed. I'm going to talk a lot about the specific project, the Maxey Flats disposal site, the closure example that I'm talking about in this presentation, and then spend a little bit of time talking about some things that we learned from the process of doing this design and achieving regulatory acceptance for our proposed solution to this site. So a few words about risk. For those of you who are familiar with risk and reliability-based design and engineering, you may have seen this figure before. This is a widely published figure. This particular one has its origins in the U.S. Army Corps of Engineers, specifically related to dam safety. And the purpose of me putting this figure on the screen is to just illustrate all the different ranges of acceptable risk with respect to consequence of failure that we have for different kinds of engineered applications. So I mentioned dams. You can see that we have this shape representing acceptable risk for dams, and you can see that that is reference to annual probability of failure. In this case, 10 to the minus 4. That means something like in any given year, you have a 1 in 1,000, 1 in 10,000 chance that you might have a failure, and the consequences of dam failures, depending on the kind of dam, could be anywhere from 10 to 100 million or more dollars worth of damage. That would be just an example of how to read this graph. But the important thing that you can get out of just looking at that one example is there's a wide range of what might be considered acceptable in terms of annual probability of failure. This is almost an entire order of magnitude difference from the top to the bottom of this shape. And then likewise, consequences, depending on what facility we're talking about, can be wildly different. And so the intent of showing this figure is to illustrate that for many of the typical facilities that we design as engineers, civil engineers specifically, there is a line below which we generally regard the risk to be acceptable and above which it's not. And that is used in a lot of reliability-based design and code development as sort of the benchmark by which we decide if our design methodology is acceptable or not. But we get into a problem sometimes if it's difficult to figure out exactly what the consequence of failure is for a given failure mode, or if it's very difficult to quantify what the probability of failure is, then you don't know where you are on this chart. And also bear in mind that a lot of these estimates of probability of failure and consequence are related to widely accepted models for how we go about designing these facilities. So if you don't have a widely accepted model and you don't have a good idea of risk, then you have a challenge in front of you, and that is where we found ourselves in this particular project. So where does tolerable risk for low-level radioactive waste disposal sites fit in that graph? So I want you to think about that a little bit as I continue to talk. And the problem that we were dealing with specifically on this project is how does the public and by extension, how do regulators respond to unfamiliar risks compared to with the familiar risks? So how do we communicate that, and how do we make decisions around unfamiliar risks? And then finally, when it comes to engineers like me, how do the professionals involved in these closure projects effectively communicate what risks we're able to quantify, and how do we go about quantifying those so that we can communicate them? So realize that we have people with many different backgrounds on the call today. So I'm going to go over a little bit of the US CERCLA process. So CERCLA, or sometimes referred to as Superfund, is a regulatory framework for the remediation of contaminated sites. And it generally follows the sequence. So we have at the very beginning a discovery that we have a problem. So in other words, a source of environmental contamination that is a threat to the public. And once we do that, there is a process that follows. So there's an investigation where we try to characterize the kind of problem we have, what it's going to impact, and what are some potential remedies for that. Based on the kinds of risks that are assessed at this stage, we would have involvement with the national priority list, which determines which projects need to be cleaned up first versus later. And that's generally related to consequence and probability of impact. From there, we get into more detailed studies to do a detailed remedial investigation, feasibility studies to really understand what possible remedies would work and what they will cost. And then from there, there's a decision that's made as to how the remediation will proceed. And it's after that stage that we get to the remedial design. And this is the point at which engineers like myself are usually involved in these projects, is when we are doing the remedial design, a decision has been made as to what technologies will be used to remediate the site. And it's at that point that detailed engineering needs to be performed so that it can become a design that can be carried out, something that can be executed. And then after the remedial design is implemented, then we go into the long-term maintenance period where we're operating and maintaining whatever the remedy is. Throughout this process, there's public participation, there's definitely regulatory participation, and there are many decisions being made along the way, as I pointed out. So some questions about that come to mind that I'm going to address a little bit when we get into the case history is what role do engineers have in this process in matching available technologies with the risk and performance objectives. Again, I mentioned that we're coming in after a record of decisions. So already some of the very high level decisions have already been made when engineers arrive in the picture. But what decisions remain, and how do we properly address the risk? How do we document performance objectives at the ROD stage, and how do those get implemented at the design stage? I think that is, it's an interesting question, and one that I think will come out in my presentation on the case history. What flexibility do we really have for new technology? And I think this is really directed at people who have a regulatory mindset in the group, because if you write a decision prior to design in such a way that you're only able to implement a single technology, then you may not be able to engineer the most optimum solution at the end. And then when it comes to addressing the underlying risks to the public, how do those get communicated in engineering criteria, and how do we ultimately make sure that our design is meeting those criteria? So before we really dive into the case history, I want to just highlight for everyone something I think is very important when we talk about lined versus unlined sites. So I had mentioned that this is an unlined site that I'm going to be talking about. So why does that matter? It matters because a lined site has a leachate collection system associated with it. So this is a picture of a modern landfill that has a leachate collection system at the bottom. And as a matter of engineering principle, it is very difficult to keep water out of places that we don't want it to go. It is far easier to collect water and give it a place to go that is constructive, and leachate collection systems effectively carry out that principle in practice. And so I would say that when it comes to controlling the risk of environmental contamination, leachate collection systems are perhaps one of the most important tools that we have at our disposal to control contamination, because we are providing a direct path for water to leave the system that doesn't involve going into the environment directly. So that's a big difference. And so there's a huge difference in the risk regime for an unlined site versus a lined site as a result. So let's talk about what we were here to hear about, this particular site, Maxey Flats disposal site. So this site is located in Eastern Kentucky in the United States. For those of you not familiar with the United States, this is in the eastern half of the country, about midway from north to south. And the site was picked on account of being fairly remote. And in the 60s and early 70s, this site was used to dispose low-level radioactive waste from 60 different sources. They included everything from research to hospitals, medical applications. Many different kinds of waste were disposed here. And I'm going to show a few pictures later on that show how it was disposed. And that's really the underlying concern for this site, is how it was disposed and what kinds of things were disposed here. On the screen, you can see what the site looked like near the time that it was shut down and started to be remediated. So this would have been the mid-70s. And it shows a little bit about the situation of the site. So it's located on top of a bluff. The surrounding terrain is valleys. And when it rains, any rainwater that strikes the site will typically run off the cover and then down into the valleys on either side. Or, as turned out to be the problem here, it can also percolate through the top of these trenches where waste was buried, and then carry potential contaminants into the surrounding surface water, which is in fact what happened. So at one point, there were some monitoring stations set up. Tritium was detected in the nearby surface water, and at that point, the decision was made that the site would no longer be able to accept waste, and it was necessary to cover it and to stop the movement of contamination from the site. So when this picture was taken in the mid-70s, they had started that process. They had begun to consolidate some of the waste trenches. They had begun to treat some of the liquid waste that had been recovered from some of the trenches on the site, and they had begun to construct a cover to try to shed stormwater from the top of the site. After that, so this is a picture that was taken in the early 2000s. They had constructed first in the early 80s, and then again replaced it in the 90s, a temporary cover, which was an exposed geomembrane. That's what's giving the black color that you see here. And that shed stormwater much more effectively than a soil cover, but it was considered an interim solution. And I'll go in a little more detail why it was considered an interim solution. But the idea was to very quickly get to a point where new stormwater percolation to the site was controlled. Some other pertinent facts about the site to help understand what we're looking at. The total area of this site is right around 25 hectares. For those of you in the US, it's about 60 acres. And it's a pretty large area to manage for a low-level radioactive waste landfill. Okay, moving on. This is what the site looked like after it had been closed. So I'm kind of skipping to the end of the book. If you're curious, we did actually succeed in building the final cover. This is what was desired as the outcome for the site, is to have a vegetated final cover over the site that effectively sheds stormwater. But the big question becomes, how do we engineer this so that we have some degree of assurance that it's going to perform its intended role, which is to shed that stormwater off the site and not continue percolation of surface water through the waste. How do we satisfy ourselves as engineers that we've achieved that objective. So I could spend the rest of my time talking about that. So here is a cartoon of a final cover showing the sort of the hydrologic process that we have for final covers, and specifically, precipitation falling on the top. That precipitation is either going to be converted into runoff or evapotranspiration in our topsoil layer where we have vegetation, so grass in this case. Some portion of that precipitation is in fact going to percolate through the soil, and we intercept that in drainage media, so either geocomposite or granular sand drainage layer above our barrier layer. And then our barrier layer is composed of a geomembrane and a clay component. In the case of Maxey Flats, the clay component was a GCL, so geocomposite clay liner. And then there's always some possibility that we have low spots where water is able to collect. And when that happens, there's the possibility that that could coincide with holes or flaws in our barrier layer, which could result in infiltration. And so ultimately, when we are talking about engineering a final cover, what we are trying to do is to limit the instance of this possibility right here, the coincidence of depressions with holes where water can infiltrate. So let's talk a little more about Maxey Flats. So this is a picture taken in the mid-70s of what the disposal practice at Maxey Flats looked like at the time that it was in operation. And so you can see a trench. So it was dug into the soil. It's also dug partially into rock. You can't see the rock in this picture, but deeper down there's weathered rock that was excavated to create these trenches. And then as waste arrived from the various sources, typically in containers like these barrels or boxes, sometimes wood boxes, cardboard boxes, they would get thrown into the trench or dumped into the trench, and then soil would be immediately pushed over with a bulldozer. And I want to talk a little bit about the consequences of this mode of disposal. So first off, to just understand the magnitude of these trenches, I've put a figure on the screen that shows a map where these trenches occurred on the site. So this group of trenches here in the west were the original trenches at the site where waste was disposed in the manner I just showed. And then there were also other things like pits where liquid waste was solidified. Those were later dug up and relocated. And these trenches down here are some of those newer trenches with the relocated waste. And then also there were these concrete disposal bunkers that were placed in this area to also handle some of the solidified waste. So several different kinds of waste disposed at the site, different physical forms, but perhaps the most troublesome would be those containers that were dumped and buried in this area with respect to potential subsidence. And that's where I'm going with this conversation. So conceptually, we have something like this. We have containers in the ground and trenches. Those containers are buried. And what we're concerned about is that at some point in the future, those containers, because they have voids, will collapse. As a result of that collapse, there will be a change in volume in the ground that will express itself as depressions at the ground surface. And we will have, as a result, ponding water, which is precisely the thing that we're trying to avoid for the performance of our final cover. So the challenge to the engineer recognizing that this can happen is how do we quantify the potential for that to happen? How do we quantify the expected occurrence of it? How do we quantify sort of the extreme occurrences of that? And that's where this moves into a risk and reliability regime. Here's some examples of what some subsidence effects can look like at the ground surface. These pictures were taken at Maxey Flats, so this was something that was already understood to be an issue. So I think it's easy to understand a very close to the surface void that collapses and creates a crater. This is, extreme example of what can happen with the subsidence resulting from a container collapse. But I think more frequent of an occurrence and more troublesome for long-term performance is actually a case like this, where you can see there's an accumulation of silt on the exposed geomembrane that indicates that we have a low-lying area where water is not able to successfully drain. So if this were allowed to continue in our final cover, then we would have for years and years ponding water over this location with the possibility to infiltrate through holes. So this is really the thing that we are focused on trying to prevent. This also, but this is probably the most pervasive problem that we're looking to address. So you can look at all of that and say, well, I don't think that this method of disposal is very good. I think this is causing a problem. Well, you have to remember the mindset for radiation safety, why you would dispose of waste this way, basically. And so I'm going to talk a little bit about radiation safety basics to understand why this would be done this way. People are not just doing things at random. So with radiation safety, we're worried about three things. We're worried about the time of exposure of people to something that's radioactive. We're worried about the distance between them and the shielding. If you can shorten the time, increase the shielding, or increase the distance, you are increasing safety. And so with this method of trench burial, they've effectively accomplished all three. So from a health physics point of view, this is precisely the right thing to do. Also, just as a matter of terminology, want to make sure that everyone understands the difference between exposure and contamination in the context of radioactive waste, because they are very different pathways for health concerns. So when we're talking about exposure, we are talking about the incidence of radiation, so alpha, beta, gamma radiation on the body. This is something that can be measured with an instrument. You can figure out how much exposure you've had. Contamination is entirely different. This is when the source of radioactivity is either on or inside a person. So we have external, internal contamination, and then they will then get radiation exposure as a result of those sources being in their body. It's something very different. So typically when you're looking at radiation workers on a site, remediating a radioactive site, you see a lot of controls for contamination. The idea being we don't want materials to leave with people who are working on the site so that they will continue to get exposed after they're no longer on the site. And exposure is just a measurement of how much radiation people have been exposed to at any point in time. So important distinction, want to make sure people are aware of that. When we're talking about tritium leaving Maxey Flats disposal site, we're worried about contamination because tritium is a radioactive source. It is mobile, is leaving the site, and from that point can get on and inside people and expose them to radiation. That is our concern. So again, we have as a basic problem these depressions shown with the red dashed lines. How do we quantify that in a meaningful way to make design decisions? So that is what's coming up. Here's some questions related to that. Maxey Flats, the final closure decision, the decision that they would go from that interim condition to the final condition, was premised on the idea that most of the subsidence had already happened. So I had mentioned earlier, they put a temporary cover on. They put a temporary cover because they knew and they expected that those containers would continue to collapse and subside. And for that reason, the site had monitored subsidence for a long time. And what they had noticed is that the amount of settlement that they were getting at monitoring points was decreasing over time. And the number of times that those craters would appear on the surface was also decreasing. And as a result of that, they made the decision that it was okay to invest in a final cover to close the site. So from an engineering perspective, we have to think about, well, what if that's not right? What if there's still more subsidence yet to happen? What is that going to do to our final cover in terms of performance? And what should we be doing at the remedial design stage to make sure that we are addressing that possibility and ensure we have adequate performance? And then going back to what I said at the very beginning of the presentation, how do we decide what adequate performance means quantitatively? What criteria do we use? And that's actually the hardest question to answer. So I'm going to talk about that. So I have on the screen a cartoon of a pyramid-shaped municipal solid waste landfill as it might be constructed using the current regulatory framework for landfill construction here in the US. And if you grade that the way a lot of regulations are written, with the understanding those regulations were written from the perspective of what has been tried in the past and what has been deemed acceptable in terms of performance. If you do that, and I focus on this flat part of the plateau on top, so typically graded anywhere from 5 to 10%, what kind of pooling of liquid will I expect to see on the top? And so I have an example of what that might look like in a model here at the bottom. I'm going to spend a little bit of time talking about how we go about modeling that, but what we're looking for is to see where these blue pools, where water is ponding on top, where that's occurring, how often, and between different scenarios, what is the risk on any given occasion of that happening? So how do I do that? So conceptually, got another cartoon on the screen. If we have a container buried down in the ground and it's a brand new barrel, let's say, then I would expect that my final cover over the top of that should be exactly as we designed it and constructed it. Water should be able to shut off, no problem. But what happens when it rusts and the voids inside collapse? And then I expect that the volume that has collapsed, the change in volume is that the barrel is collapsing, will be projected to the surface in this cone shape. It's going to manifest itself at the surface in the form of one of those craters like I showed earlier. And as the final cover moves into that crater, we're going to have these depressions where water's ponding. That's the mechanism. What can we do about it? We can, of course, make our slope steeper so that water is able to drain more effectively. We can make our final cover thicker so that this depression has to be projected over a larger area and will essentially blunt the impact of that collapse. And then I can also do one of the things that we did in our project, which is to reinforce the final cover with a tensile element, a geogrid in this case, which is going to spread that depression over a larger area. I think this is a really important distinction. When we reinforce covers like this, simply because of the magnitude of the areas we're talking about, we do not prevent these voids from expressing at the surface. What we are doing is transferring them over a larger area. And there's a modeling activity. We have some publications about how you would go about quantifying that. Not going to go into the detail in this amount of time that we have today, but there is a way that you can quantify that spreading. And in the case of Maxey Flats, we actually did 2 different geogrid layers. We had one near the surface to deal with the very large, very shallow craters. And then we did one deeper down to bridge over some very localized depressions that were creating like that very deep discrete crater that I showed earlier. So we have both mechanisms addressed with this design. How do we go about quantifying the surface depressions over a 25 hectare area? We didn't do it barrel by barrel for 2 reasons. Number one, we don't know where all the barrels are. And most importantly, we don't know in advance which ones are going to collapse and when. And that's why we go to a stochastic or probabilistic approach. To make this manageable as a problem, because we need to do many hundreds of realizations, we made a very simple approach to quantify this. So we look at discretizing the entire site, all of those trenches that I showed on the map earlier, into these rectangular columns. When we have an incidence, a modeled incidence of a collapse, that means we have a change in volume in that column. That change in volume gets projected to the surface. This is the only equation I'm going to share during this presentation. If any of you have been involved in tunnel engineering, you will recognize this equation. This is a simplified model that we use to project what craters will occur at the surface when we're tunneling due to a change in volume down in the ground. And it's basically projecting a normal distribution to the surface where whatever change in volume we have at depth is realized at the surface over a larger area that has this bowl shape to it. And so that's what this equation is doing. And what we've done in our model is to look at all these different columns where we have collapse, changes in volume, and then we sum those effects over the entire footprint to see what the gross change in the final cover geometry will look like as a result of those collapses. Now, here's the key piece. Because we don't know where all the waste is buried, we don't know all of its properties in exact detail, we have to try out several different possible scenarios. This is where the stochastic modeling comes in. So we will, within a rule set that we generated, assign different changes in volume across the entire footprint, calculate the final surface shape, calculate how much ponding occurs, and then do that again and again for many different random configurations with the idea that we are trying to figure out what the extreme cases are where that result in the most adverse drainage, but also what are some of the more typical cases that can result. The rule set we use to generate that random field is based on measurements both at Maxey Flats and on the occurrence of craters at sites that have similar waste. So we looked at other sites, we saw what's the occurrence of these craters, their depths, how does that relate to the volume of material that was placed, the age of the waste. All of those components can be taken into effect to project into the future how we think the site will behave. And of course, every one of those trenches were different. So we also have all the specific geometry and waste inventory for each of those trenches to consider to the extent that that information was available. So if you go through that exercise for that cartoon pyramid I showed earlier, you can come up with what I'm calling a reference criteria on here. So this chart is very important. This is the criteria. What we show on the bottom is the percent of the total area that we're designing over, how much of that is flooded to 30 centimeters depth of water or less. So if you have 0.7%, that means that 0.7% of the total area is flooded to 30 centimeters. And then as you move to the left, you can see that there's less and less area. And then on the vertical axis, we have cumulative relative frequency. So this means between all the modeled cases that we performed, so all the stochastic models we generated, how many of them resulted in this amount of flooded area or less. So you can see this graph is curving up towards 100% as we get to the higher flooded area. So that means that by the time I get to 0.7% flooded area, that means in all of our simulations, at that point, we had covered pretty much 100% of the occurrence of flooding that we would see at 30 centimeters. So we won't expect to see more than 0.7% in our model, but you could see it. So at the low end, only about 25% of our models had 0.5% or less for this reference case. What we want to see for design purposes, if we say that this reference criteria, this is the acceptable amount of ponding that we can have on a landfill cover, what we want to see for any given design, that what we're projecting for a specific site should have less than this amount of flooding. And so the criteria is that we want to plot these bars to the left of the line, and that's what I'm showing here. I'll explain a little bit more how we went about doing that, but the idea is for any given percent flooded area, we want the cumulative frequency to be higher than this line, because that means that more of our cases had this amount of flooding or less, as opposed to having more flooding. So that's how the design criteria is applied. So I realize we're a little limited for time, but I wanted to put the spreadsheet up to illustrate something about this effect, or this process, how we go about doing this design. So right here in the middle is the most important part. Do we decide if our design is acceptable or not? I just talked about the acceptable settlement criteria. That's this input right here to our design. What goes into modeling Maxey Flats as a site includes looking at all the available data that we have for the site, figuring out what kind of future volume loss we could experience, modeling that for individual scenarios, figuring out what the post-settlement drainage looks like, and then comparing that to the settlement criteria. And we keep doing that again and again, changing things like the slope, the reinforcement, the thickness of the cover, until those combination of factors give us the passing design. So this is just another way of stating what all engineers do when we do our design process. It's an iterative process going through different analyses. The difference that we're introducing here is the stochastic model of differential settlement. So what does that look like? We all came here to see pictures, so that's what I'm going to do next. So some example realizations. This is a 3D image of the results from our model, and I am showing settlement as shaded areas. So what you can see, this is realization 22 out of a run of 200 that we did for this particular model. And what you'll see is where these trenches are. So I showed that trench figure earlier. We are expecting a certain amount of settlement. You can see that expressed at the surface as these depressions. There's quite a bit of vertical exaggeration on here to get those shadows to turn up, but that's what we're trying to see. The other thing we're looking for is you can see that where these depressions occur, it's irregular. There's little craters and depressions in it that is a result of this random waste disposal, random occurrence of collapsing containers. That is something that our stochastic model is able to do, and that's why it's important that we do this in a probabilistic framework, because if you just sit down and take the average case, you wouldn't see these craters, and it's really those craters that create the possibility for ponded water. So here's another realization. You can see a blue area that we have that 30 centimeter or more ponding. So that gets counted in the total. Here's another realization. You can see more ponding. You can see this other realization, the ponding is occurring in different places. So that's part of our modeling activity to look at what are different possible ways that this could occur in the site, and so on and so forth. So we did that for several hundred cases. You add them up and you look at the cumulative frequency, and the goal was to produce a combination of those factors I mentioned that will give us less flooding than our reference criteria. That would be considered acceptable from a risk perspective. And that is, in fact, what we did, what we presented to the US EPA and the Kentucky Department of Environmental Protection. And they accepted this methodology and that rationale for the design. The important thing to keep in mind is that because prior to this project, there wasn't an accepted methodology for doing this kind of design, figuring out what an acceptable slope is, the state of practice at that point had been to go with a prescriptive final cover slope. So let's say 10%, say that's good enough. But the problem is there is a tension between what is good for drainage and what is good for erosion. So if you go to a steeper cap, you have more potential for erosion. And this particular final cover was meant to last hundreds of years. So we want to make sure that we're balancing the constraint of limiting erosion against the constraint to have good drainage. And that's why having a quantitative criteria was so important for this particular site. But the challenge was how to come up with that. And what I presented to you is a methodology to come up with a criteria, and this criteria was accepted. Final word on Geogrid. So I mentioned earlier we put a Geogrid in there. What good does that do? So this is a way to quantify the benefit of having a Geogrid in the system, and it's simply for the same scenario. By spreading that differential settlement over a larger area, we are limiting the depth of ponding that can occur. And so you can see my blue zone where ponding is occurring is larger in this top image than it is in the bottom image. That is quantifying the benefit of having that. I think it's really important, again, to understand that the Geogrid is not magic. It doesn't make the differential settlement go away. What we are doing is we're spreading it out over a larger area, and you can quantify that benefit using this technique. So before I go to my conclusions, I want to share some photos of what this looked like when it was being constructed. So I think it's important to understand how these get built. So what I'm showing in this photo is a picture of one of our layers of Geogrid that had been deployed above the geomembrane. So you can see the geomembrane below. You can see that the Geogrid above, it's oriented in the direction where we're expecting the major depressions to occur across the trenches. And then you can see in the background trucks that are deploying soil. So you have trucks dumping on the area where soil has previously been placed. And bulldozers pushing and deploying that over the cover. So this is the cover system going on. You can see, just stepping further back, what this looks like. This particular part of the construction was actually when we were deploying soil over the interim cover. So the interim cover is visible here in the foreground. You can see it has that very irregular shape. The final shape of the site was a more regular hill that had very straight slopes, anywhere from 4 to 5%, depending where you are. And here's a view of that layer of Geogrid I mentioned earlier that occurs right underneath the barrier system. So here's the Geogrid being deployed. You can see the GCL and the geomembrane going over top. And then here's a view of the Geogrid going in at the sides of the interim covered area. And then final cover going back over the top, so the final cover soil, and then the final configuration of the site. So this is what it looks like when it's all done. So once that last layer of soil goes on, it was vegetated and protected from erosion, and then it all grew in. This aerial photo was taken just after the site was capped, which was in 2016 when we wrapped up this work. And you can see the permanent stormwater conveyance structures around the side. So what do we learn from doing all of this? Obviously, there's the technical matter that I presented, and there was a lot of work that goes into figuring out how to do that. But I think from a bigger picture, taking a step back and looking at the CERCLA framework, there's a lot of assumptions that go into making closure decision documents like that ROD that I mentioned. And there isn't a need to connect those objectives, so protecting human health and safety in the environment from this contamination. There's a need to link that up with the remedy. In this case, they're worried about percolation of new stormwater. There is a need to have that directly connected to the engineering of the final cover system. If you're going to do something like what we did, to try to balance the design constraints of erosion versus drainage, slope stability. We need to have quantitative criteria, but we don't always have quantitative criteria. Things like final cover slopes are largely prescriptive in this country right now, and I suspect elsewhere. But if you're going to engineer it and you're going to present that to the public and to the regulator, having a clear quantitative criteria is much better. Things like Geogrid can save cost and improve performance. But again, we need a way to show what benefit that has. On this project, we have a quantitative framework that we're able to show that benefit. So it's not just a matter of putting in the section and hoping it works, but rather trying to use our engineering principles to show how it will work. And I think that's important. And I think when you're in a novel application like this, I think we really need to seek out ways of doing that. And of course, falling back on other studies, bench studies, full-scale studies, the histories that I mentioned, to validate that those are in fact quantifying correctly. But it's important to do that. And this is a case history of where we did an implementation for a design methodology that was not off the shelf. It was something that had to be developed for this purpose. And I believe it was the correct implementation. So with that, I very much look forward to your questions, and I hope everyone came away with something new from this presentation today.
Yeah, thanks, Kevin. So it's an excellent case study. I would request all the attendees to type their questions in the chat box if you can. Yeah, happy to see that reliability-based design was used in geoenvironmental engineering practice. Probably, you might have faced challenges of educating the regulators on these advanced concepts and having them buy into it. So I would like to know, what challenges that you faced dealing with the US EPA and the Kentucky Department of Environment in this new analysis approach. And
Yeah,
one other thing I was wondering is, so now, you showed that the CAP is designed and constructed. Are there any monitoring programs going on, just to evaluate the performance of the cover? And of course, also the overall, the facility?
That's a great question. So they're actually related. When these designs have typically been done for other sites, the prevailing practice is that you will construct a cap, typically using some prescriptive guidelines for how you will slope it and proportion it. And then you will use what is known as the institutional control period to look and see if depressions are forming. And if they do, you go out and you fill them so that the cap drains satisfactorily again. And so that is kind of the state of practice typically in this business. So what we were trying to do with this project is to, as you said, educate the regulators to say that it's not enough to just rely on the institutional control period. We want to try to avoid unnecessary maintenance by anticipating in advance what kinds of depressions we may encounter. And so really the challenge was to try to convince everyone involved that we had looked at enough data from similar sites. We had looked at enough data from this site to really understand what the incidence of subsidence would be in the future and what the magnitude of that subsidence would be. So our model is not so much making up the future as it is using what observations we already have and structuring that into a theoretical framework that can be applied across the entire footprint. Because if you see a crater in the ground, all you know is you had a crater in that spot. What's the cause of that crater? Why did it happen there? How might it happen again in the future in other places? That's where we're kind of out in our own analysis, but it's rooted in those observations. And so what we had to do is to educate the regulators on how this framework, this theoretical framework that we had constructed, is able to successfully convey that past experience into future projections of performance.
I think, that my experience is also the same. Like, if you can take the regulators along with you, as long as you're rational and, the technical or science-based, so there should not be any issues for them to accept or follow you. But, Kevin, can you look at the chat box and see if there are any questions that are asked? Go all the way to the top and then see as you scroll down, see if there are any questions that you want to answer.
Okay, so there's a question here: if we use biaxial or triaxial grid, that's an interesting question. Okay, so we actually used a geogrid that was biased in one direction. So it was actually a sort of a uniaxial grid for most of the reinforcement. And the reason is that because we knew the orientation of the trenches, we knew where the most adverse subsidence direction would occur. In other words, if you stretch the grid in the strong direction and the short direction across the trench, you were going to be more successful in blunting subsidence than if you oriented a uniaxial grid the long direction down the trench, where you don't have this zone to anchor into that has less subsidence. Triaxial grid, my understanding, is primarily used for subgrade reinforcement, where you're looking to spread out very localized discrete loads over a larger area, and for the purpose of limiting transient deflections, and that's not what we were trying to do. These are very long-term deflections that we're mitigating that are going to be present for decades and centuries. But it's a great question, because it's not easy to see from the photos exactly what we had there if you're not familiar with GeoGrid. Okay, yeah, what kind of monitoring? So this is the same kind of question. So what they do at this site, there are two technicians who essentially work every day at this site, and their job is to walk the site and look for signs of distress and to document them, to survey them, and to map them. And if it looks like that will impair the ability of the final cover to drain, then they have to go out and at least fill in the superficial ponding. But if it gets to a point where they have very extreme prolonged ponding, they're probably going to have to go out and actually exhume that part of the synthetics and rebuild them. To my knowledge, so far this has not taken place, but keep in mind, we finished in 2016. There is still many decades ahead of institutional control for this site.
Kevin, can you stop your share screen so that we can see
Sure.
you answering questions?
Okay.
Look at additional questions in the chat box.
I'm looking through the questions. A lot of kind words from people, so thank you for listening and for your kind words. Okay, so I have a question about how do we remove leachate? Are there any new technologies, or what was done at this site? So I will speak specifically to what was done at this site. So because it's a known problem that we have surface water infiltrating into these trenches and then carrying contamination away, there was actually a period of about 20 years where vertical wells were drilled at hundreds of different locations throughout the trenches and water pumped out. It's not as good as having a new leachate collection system on the bottom of the trenches, but because these trenches were already there and already buried, this was a remedial technique used to try to control the water that was already there. Ultimately, the best way to control the leachate in this case was to prevent new leachate from being generated, which was the purpose of the cap. In terms of what other new technologies are out there, we're really limited in terms of what is capable of drawing water out of the ground. So you're looking at wells, you're looking at trenches, you're looking at under drains. These are the technologies that you see used for this purpose. So I have a question about what's shown in the horizontal axis and percents on the graph. So I think that's talking about the design criteria. So again, very briefly, when we go from 0 to 100% on the vertical axis, we're talking about from 0 to 100% a tally of the different cases that we ran, the different scenarios. On the horizontal axis, the percents that are shown is how much of the total area, what fraction of the total area was flooded to 30 centimeters or deeper is what we showed on there. So as you move from left to right, you have more severe flooding, and cumulatively that covers more of the cases that were modeled. So as you move to the left, you have less severe flooding, and it represents a smaller fraction of the cases that we modeled. Some other kind words. Will groundwater in the surroundings be monitored to ensure there's no infiltration? So yes, this site started being monitored in the 70s. That monitoring continues to this day. And I believe the institutional control period is measured in decades. So that will continue for many years into the future. So why not use a non-collapsible material under the cover instead of barrels, empty caissons, for example? So yeah, it's an interesting question. So for the waste that was later dug up and solidified, they actually did use reinforced concrete caissons to bury that waste. And those, of course, are very well defended against future subsidence. The problem is the waste in place that was deemed to be left, or decided to be left in place and not touched again. So for environmental reasons, for cost reasons, the vast bulk of the waste mass in place that occurred in collapsible barrels was left as is. And our objective was to cap that in an effective way that would allow them to remain in place. So things that might be non-collapsible that we could use under the cover, for example, we could like put a reinforced concrete roof over these trenches. That was considered. It was deemed cost prohibitive, considering that we also could offer this combination of slope and reinforcement that could achieve the objective acceptably. So again, that's where that quantitative measure is important. Can we achieve our objective reasonably for the available cost? That was a big part of this, and that's a big part of the involvement of the state. So a little more background on that. The state in this case actually had two parts. There was the regulator part, and there was the part responsible for the environmental cleanup. And because the one responsible for the environmental cleanup had an interest in reducing cost, they're kind of at odds with the regulator. So they're two completely separate groups of people. So the regulator part was the ones that we had to convince that we were meeting the objectives. The group that was responsible for the cleanup, we had to convince that not only were we meeting the objectives, but we were doing it in a cost-effective manner. So it's a good question. That's the challenge we're dealing with.
There are a lot of questions, Kevin. So
Yeah.
just whenever you want to stop them, fine. You have been talking for a long time.
Yeah,
I can always share this chat box file, and you can contact them. Whatever. Can you look at it and select a few more questions?
Yeah, I've got two more, and I'd like to answer both of these. So one is waste inside the containers vitrified? So because this was an old site, that was not on the minds of the people who disposed of waste. They were simply trying to isolate the public from the waste as quickly as possible. So there was no waste preparation other than placing it into containers that was done at this site. For future waste, that of course is a very well-known method to prevent subsidence, but unfortunately not one that was followed in the 70s. I have a question here. Did we look at factors related to the hydrology of the cap? So things like drainage and flow, evapotranspiration in the cover to impact the ponded area? It's a great question. So we did not model in detail the hydrology. We in fact took the stance of a worst case where no water is able to drain at all. And if there are any depressions, we assume that they will flood and therefore be available to infiltrate the cover. So it's a great question because in reality, the final cover system, considering the entire hydrology, is less adverse than what we modeled. But that was an important assumption for us to look at the consequence of depressions, because we wanted to take the stance that if there's a depression, it will be a problem. But yes, as the commenter pointed out, it's not guaranteed because we have the whole rest of the hydrology to consider. And